test. So the goal is still the same. The super search engine. And I thought about it even more, and I think it's possible. Using a compressor to make a smart index of a huge text does the trick. With some clever multi-level sorted data structures, we get near instant search results. And the new engine actually is super fast, but it returns no results. This is another little error. But I screwed something up here. It's super fast, it's way below a millisecond, but the result list is empty. And now we have this other bug here. Oh, that's nasty stuff. Yeah, it's in the middle of being reorganized. Let's do the systematic test first. Let's say we take all combinations of A's and B's, up to as many characters as we can afford, because it gets exponential fast, quite obviously. Yeah, let's take a random window. Let's say we put in a 5. How many A-B combinations of length 5 are there? Any math wizards? Yep, it's 32. A, B, A, B, A, B, B, etc., etc., etc. So we take all these combinations as our master text. And we take another combination of letters as our search query. What the heck was this overlong queries? Oh yeah, it's searching something that's longer than the full text you have. Yeah, it's good to test, but it makes the search even slower. I'm not even printing the texts anymore because it's so much. Here I throw away the results, I mean the print output. But I think this new searcher can do this by itself. Okay. Something like this. Here it is. I'm working on this website to share background music, basically. It's going to be called actual background dot, one of the top level domains that I use. .website. Yeah, actual background dot website. That's pretty cool. These flying cars. That's nice. So whenever somebody streams, for example, and they want some background music to be played, they can not just turn on this background music on their machine and stream it, because then they get copyright stricken. Copyright slapped on the head. So I propose we make a different website where you just enter your music wish, like as a YouTube video, and people will just over this other website open the YouTube window and have the full experience of the website. It's a trick to circumvent copyright without infringing yourself. It's kind of watertight, I think. We should make this website in one of the next sessions. Yeah, let's post the URL. I'm quite happy with my ideas lately, they're pretty good. What does the searcher return? The searcher returns a collection of int pairs. Yeah, so I was right. And we want to sort this actually. Then we check if it's correct. So this is the text for the test for the search engine, and it prints how many different combinations were tested. So if this here works with a reasonable length, we can be pretty sure stuff works. Yep. I guess it's slightly different syntax. Failed. Oh, it's a little more involved. It expects compression result, not just the text. Yeah, how did this work again? Oh, okay, I remember. Too many windows. That's old. This is the one. So here, the version 3 searcher requires an object of the old type, basically an instance of its predecessor for the data structures. But it has its own methods of searching. Pretty cool how they collaborate. But it's still not going to work because this one expects... What does this one expect? You have to call a function, I think. It's not so easy. Oh, we have to run the compression first of all. So we have this random string of A's and B's. First thing is compress the text. Let's see, byte mode, I think. Let's go all the way here. Make a new compressor, set some flags. There's a cool new mode, it's called balancing, we should use that one. Makes the brackets that are made in the compression more balanced, which means they don't all lean to the left side or to the right side, but they form like a tree. This makes the search faster. Uppercase doesn't matter. Okay, I think like this. A lot of boilerplate. Oh, we make the searcher once per text, not once per query, of course. searcher database, searcher 1, and the actual searcher. 1. Okay, slowly getting there. I made so many classes in the last days. They're also abstract, so maybe this one is actually the one I want. Yeah, that looks very promising. Compressor. And the text, oh my god, yeah, finally. Okay. Why do programs not write themselves? Why do programs not write themselves? Question mark. Okay. Yes. Almost there, ladies and gentlemen. Almost there. Test function compiles. Let's run it. Oh, it wants a maximum number. Like how long is the text going to be that we search? How long is the query going to be? Okay, and it fails right away. That is nice. There's a verbose flag. How about we set this one? Testing length 0. So if we search in a 0-character text, everything works fine. Now we test length 1, and the query is the character A. And A is contained in A, that's okay. Every time it says okay, the algorithm has worked. Okay, it has worked in both these trivial cases, or almost trivial. Now the amazing case, looking for AA in the string A. It should fail. Does look like a bug, but no, it's not really a bug. It's finding the A and it thinks, okay, let's look in the area. But while it looks around the area, it finds out the string has ended and it fails hard. So that's fixable. We could simply just have this function fail. Yeah. Or no. Let's fail here. Let's fail. When did you hear that? Okay, if we are something like this, go from here to here. And if that is beyond the array, we are unhappy. We could do the same thing here for the first array. I think that was a fix. Let's try again. Integer.size not found. That has to be an actual bug. Yeah, that was bullshit. Why didn't anybody tell me this? I took the length of an integer. Okay. Now the algorithm fails. We wanted to return 2 results and it returns only 1. The algorithm as I made it is not complete yet anyway. It takes this compressed query, this analyzed search query. For example, if you search for category in this Wikipedia dataset, it comes up with this 3 symbols, CA, TEG, ORI. That's the result of the query compression. So then I search from here upwards. Upwards means in the direction of the full text. I look in the index, where is this fragment used in the text? But one thing I do not consider is that we might want to split this also. Because somewhere else in the text, this might be expressed as this. No, it has to be something else. For example, this. Yep. Somewhere in the text, this might appear. A different symbol for this and this, which combined gives the same string, but it's not identical to these 3 symbols. So these 2 representations of this one word are incompatible in a way. If we find this representation, we have not found yet this one. So if we scan through our great index, we find all the instances of this, but we do not find all the instances of this. It's maybe, I'm not sure how often this appears, this problem. But in certain cases it might be very common. For example, let's say you search for this query, closing bracket, opening bracket. This is so anti-cyclical, this is anti-natural. Natural combination is this and this. And if you search for this, you are searching for something that's always sitting between, like right around the boundary. The string is found here in the middle, so we are straddling 2 units here. That's a difficult search. While if you search for this, that would be an easier search in a normal text. You know, kind of text normal people write. So this reconstruction step from here to down here, this is also something I have to write. I'm almost done, I think. Basically, it's just another search. We start with the individual letters. We start with this and this. This representation of the word. And then we look for instances of this and merge these. And we find all the possible groupings. Yeah. I hope this is all worth it, but I think it might. I found some clever tricks to make each step of the algorithm really fast without blowing it up like infinitely. it's still gonna be like a gigabyte index or something. Probably, we will see. But there's something really smart about it. Do a straightforward compression of the whole input first, and you have done the work. The search turns into finding, basically, almost. Every search is still a little bit of a search. But with this 1 millisecond, we have, what do we have? If it's a 2 gigahertz machine, we have 2 million clock cycles, 2 million machine instructions. It's not technically true, but it's roughly our budget. So if we think in slow instructions like a memory access or a mispredicted branch, then we have maybe 10,000 these heavy instructions as a budget. So for every search we can do 10,000 random array accesses, or yeah. Reminds me of the old times, coding on the Commodore 64, where you had 1 million cycles for every second, and you tried to do live animation and stuff. So challenging. Today we have fast machines, but we still have to make good use of them. So yeah, the search algorithm is not complete yet anyway. Kind of tough to program, but it's also really interesting. What if this is a standard algorithm that just wasn't discovered?